I think the mic is not connected because I can't hear. Uh,
So I have to repeat again. Uh, Good morning and welcome to this. Yeah, Good morning and welcome to this 3-day symposium, which we are organizing in honor of Professor Mrinal Ghosh, Professor Basudev Datta, and Professor Tangavelu. And also welcome to the department, as I said in the beginning. It is the we are organizing this in this hall because of lack of little facility in our department, which I promise that online people can hear me. Yeah, can hear. So promise that we will have this facility in 1 year time in our department, most probably. Yes. And about their contribution and other things, we will hear more about it in the reminiscence session today in the at 4 o'clock. And everyone will have an opportunity to tell about their thing. But more than that, more than their research contributions, all three of them worked very hard to make this department as it is today. And this contribution, so to appreciate and congratulate them for this contribution, but we are really organizing this symposium. And now we can proudly say that our department is one of the best department in the country, covering a wide spectrum of subjects. Though we have to fill up certain areas, still it's lacking. But we hope to do it in the next decade or whatever it is. I'm sure the younger community will work hard the same way these three seniors worked. So we'll talk more about them, about their contributions, about things later. But for me, I miss them in the department because especially Ghosh and Thangavelu, we joined as students in TIFA camp. So we were my PhD mates, and the personal relationship which you develop during that period is much more than the relationship you develop later during faculty hours. So I don't want to take much time now, maybe in the afternoon. So I request Professor Shrikant to chair the complete proceedings of today. Thank you and wishing all of you the very best after your superannuation. Thank you.
Yes, it could take a bit to get used to this. Good morning, one and all. So we'll try to catch up a little bit on the time as we go through the day. Um, it's my pleasure to welcome Gopal. Gopal has been with us, so who better to start off this program than our somebody who has been associated with us for very long. And Gopal will be speaking on the topic is right here. How likely it is to reach a target of GDP in a few years' time? Gopal.
Well, thank you, everybody. Can you hear me? Yeah, I think. So thank you, everybody. It's a great pleasure to and honor to come here again. So it reminds me the old days when we started this working here. But today it is a very special day. I mean, because one of our colleague who we joined together is, about to be superannuated. In fact, two of my colleagues are here already. So, in fact, this work, let me get back to the work and we will talk about in those things during the reminiscence period. Uh, this work actually we Mrinal, I and uh, Pranav Das, who is another person, I mean PK Das, as you see, uh, we started talking about long time ago about uh, if we wanted to set a target to reach certain certain level the economy in 4 years 5 years time, because which is the usual mandate for the political system, because in 5 years time you change the government and you sort of get for the re-election, etc. So you have some kind of targeted approach for every government, not only here, for other country, everywhere. So we thought we would like to see from the realistic model or some model which is often used in this area, how to set up a goal and sort of try to see whether it is achievable or not. Okay, so that's the things we talked about, and we talked about taking the approach of uh, forming as a control problem, and then try to see, because Mrinal is here, so we sort of thought that's the probably right approach. And thing is that I should mention, because I am taking a little more time to introduce this one before really getting through, but I'll quickly go through the slides, etc. That's not a problem. I'm trying to mention this. This is kind of difficult in a way. See, the uh, person like Mrinal Ghosh, and so he talks about in terms of control, etc. Right? It himself doesn't work in economics and econometrics in that area. The problem is that so we have to sort of get into with the people who can talk about the economy, what sort of variable is important, what sort of policymakers decisions can be, those things. That's why uh, Pranav Das actually comes into play. That means he actually is an economist, macroeconomic person. So he knows about those all those nuances, what sort of things then. And of course, there is a huge kind of computation around, because we work with the real data here. That means we have a data of size like uh, you know, say like about 20 years from 2000 onwards, 20 years data, quarterly data. So in the quarterly data, we sort of estimate those things. And when you talk about the only 80 set of data and huge number of variables, then a statistician is usually needed. So there I have little role to play. But somebody has to work it out, right? We have to find someone. So here is Anish Parvez. So he has actually took the trouble of learning these things, all three subjects together, because he's a student, so he had to learn. So we found him, and he actually learned in last probably 10 months or so. He put enough effort learning some control theory, learning econometrics, learning dynamic programming, all those things. And also some, of course, he's a final year MStat, he was a final year MStat student, now graduated, happily working, but still he worked with me till yesterday night, till around 12 o'clock. He sent me the slides. That's what I'm presenting here. So, so I'm immensely happy that we have found this student, Anis Parvez. So, and he has done a tremendous job, but still some more things to do. I mean, we still kind of unfinished way. I mean, we'll see. So this is the background. So country's economy is driven by huge number of variables, as you know. I mean, it is really hard to sort of say which is not important. Of course, there are some statistical decisions and things like that. Here we worked with the main around 7 or 8 variables, really. Some are policy variables, some are state variables, what we say. And sort of, and that way, we sort of say that then policymakers, there are two kinds of policymakers are here. So one is central bank, one is the government. Okay, so both are important. I mean, and supposedly we have the independence of powers to do both the both the policymakers. So that's the things actually we have to use here. So, uh, so brief introduction is that an example target. So goal to make India. I mean, it not necessarily be India. Some any country could be just can be used here. US $5 trillion economy by 25-26. Policy variables here are the whose values can be fixed by policymakers. Example: repo rate, money supply, cash reserve ratio. So repo rate actually, I think by now probably be knowing everybody that central bank fixed the repo rate, which is the repo rate is the rate the Reserve Bank lends the bank, commercial banks with that rate. So so commercial banks borrows the money from the Reserve Bank with this repo rate. So Reserve Bank actually increases or decreases the repo rate according to whether inflation is very high or very low, etc. So if it is very high, then they like to increase it. So that money's liquidity of the money gets lesser and lesser. Money supply is also Reserve Bank things, and yeah, cash reserve ratio also RBI, I mean central banks purview. So I need to formulate model. So here is the simplest simple linear econometric model. Here econometric model in the sense that Z actually are the state variables we talk about, and U's are the policy variables we mentioned. So this is the simple models, and we sort of have a this epsilons, which is noise vector, and we formulate that cost problem. That is basically this is. So whenever we talk about formulation of control problems, as you know, that there is a cost function which we call LT, quadratic cost function, very simple formulation, so that we can actually find out a closed form solution, so that we can run the actual data on these things. So econometric modeling, actually I will just go through briefly, nothing much here. Here we want this process to be stable, so that we can estimate this A1, A2, etc. All are a matrix really, these things, because YT is a YT itself could be a multivariable here. Okay. So that's why it's called variable. So let here also basically co-integration. So basically simply saying that suppose some variables are not stationary, then we sort of says few variables may be together, linear combination of them may be stationary. So here we wanted to make things ultimately transform variables to be stationary, so that we can estimate those parameters. That's the important part. Okay. So original variable like GDP, etc. are not stationary, but we have to transform it. We transform those things so that those things make stationary, and then we can estimate those coefficients. So that's the. So let me go through these things. You also know this dynamic programming very well, much better than me. So here's the dynamic programming formulation. So we sort of set up the cost function, and then actually find out the this minimizing the cost, and actually then solve it backward. So mathematical formulation of our problem is something like this. So here we sort of say that okay, YT is our state variables. Again, we come back to that. YT is our state variables, and U's are policy variables. Okay. So here there are quite a few. We sort of say var PS model, as if that there are P many state variables. I mean, sorry, not P many state variables. P many lags are there, and here also there are S many lags in policy variables. So basically, YT itself, that means today's GDP perhaps depends on there are last year and in at least 2 years of lag it may be taking, because it depends on what happened last year, what kind of performance happens, and then what kind of infrastructural, um, uh, I mean, investment was there, and what sort of other kind of things were decided, policies were decided. So that's why policies and all the state variables had to have a lags to do that. So that's why, importantly, I just wanted to mention the dimension increases, because this YT itself is a multivariable, as I mentioned, but their dimension also would be increased. Suppose we take last 2 years of lags, that means how many quarterly would be 8 or 7, 8 lags, right? 8 lags, and then you see that there are maybe at least 4 to 5 state variables. So you stack it there. YT itself consists of 4 to 5 state variables. Yeah, X actually here is the U. That was a typo. Thank you. So so that's why YT is basically stacked here. That means YT is sort of, let's say, 4 or 5 variables itself, 5-dimensional itself. And so you have, let's say, 8 times 4, 32. Okay, 32 many these MIs are, let's say, 8 of them. The P is 8. And similarly, use policymakers also 8 or 7 or 8 variables lags are there. And there may be 3 or 4 policy variables we worked with. So again, there are how many? So let's say 24 to 32 many variables. So altogether, there are maybe 60 to 70 variables we are talking about. 60 to 70 of them we are talking about. And we have only 80 quarters, I mean, 20 years, so 80 quarters of data. So that's why you see that this is kind of challenging. Actually, whenever we presented this to in front of our econometrics audience, they said, no, you are not going to get anything. I mean, of course, our things are erroneous. I mean, with that limited data, we don't have. But the thing is that it's not question of a limited data. Shouldn't we, or couldn't we take more data? For example, like another 20 years or another 40 years of data? We could have. Only problem is that those may not be as relevant. You see that our economies started opening up in 92 or 93, around that time, right? So the past data may not be as relevant at all. I mean, all the policies and the state variables were behaving differently that time. So relevant data is only limited, maybe 20 to 25 years of data we have. So that's what we have sort of used here. So you must have seen those things. So usual things comes in the after. That's why I'm saying that it is a lot of work for Anish Parvez to learn these things actually, and learning the computational things about the stacking up those variables and then getting back to original things after solving this one. So anyway, cost function is quadratic, as you see that this is sort of standard in terms of the original linear quadratic framework. So we saw this MK, DK and FK backwardly when we minimize the cost here. And that's the solution, but that's not the important part. Yeah, data exploration. So let me, we sort of use the data, yeah, as I said, that 25 years of data, kind of 96. First year of 96 to quarter to 21. So that's the 25 years of data we could take actually. So policy variables are repo rate, government final consumptions, and government capital formations, and the base money. Base money is the money in circulation. So these are the 4 state variables we have taken. Oh, sorry, 4 control variables we have taken. Those are policy variables. So so as you see that out of the 4, 3 are in central banks actually control in some sense. So money supply and all that. So state variables are GDP, real exchange rate, export based things, so which is also important here. And interest rate, this is basically we have used a 10 years government bond. So that's as interest rate. And GDP deflator, that's a proxy for inflation rate. So GDP deflator is basically inflation rate, as you can think about. So that's the inflation. So that's also a state variable. So basically, idea for the government is to increase the, get the better things of economy and actually good stable exchange rate. That's the idea. Not too high, not too low. You know, if my rupee goes low, rupee devaluates, then the export is cheaper. Export is better, but the import is costlier. So on the other hand, if rupee increases, then export gets less attractive, but imports becomes better. So that's why you have to sort of balance it. You have to sort of have a stable exchange rate is better for the economy in some sense. But of course, so that's why the inflation is, of course, we are all going through that. We have a huge inflation rate nowadays, and so whatever improvement we see in the salary, etc. Sometimes we say that it's probably, or also, common person people's actually thing is the food inflation that's probably very high. So those are the state variables we wanted to have sort of some kind of stability in there, as you see. So let's see here some of the trends in GDP. So this is the growth plans during 2007 and 8. So this is like here, as you see. Oops, I hope. Did I? Touch somewhere? Okay. Oh, thank you. Smart boards, much smarter than me. So here, so as you see that India recovered relatively better. In fact, 6 after 7, 8, so 9, 10, 11 have been doing well. These are the annual growth rate, the growth rate as well. And as you see that it started increasing a little bit, and of course started decreasing after the you remember this one, right? Demonetization. So this is just the data. I'm not mentioning anything here separately. This is just a real data from this. So, and that last plunge was due to the COVID. That's the. So India recovered relatively fast after 2010. That's a good factor. But among the other things, that's right. So we have talked about this. And then government consumption increment rate. So these are also rates. So government consumption decreased and decreased a bit in around 2000 because that was the difficult time. If you remember, I don't know whether you remember, during the 1997 to 2000, we had huge, actually, we were a huge short supply of foreign exchange. The government didn't have enough money to buy petroleum or petrol for probably next 2 months or 3 months or 5 months time. Also during the late period also 91 is also, we haven't had that data for 91. We have only data after 96 onwards. So yeah. Ruble crisis, that's also another. 97 onwards, there was huge problem. That time it was, I think, LTCM crisis, ruble crisis, and South Africa also, there was some, Brazil also had huge trouble. So 97 onwards, there was huge trouble. So that's the time, I think, there was government consumption also dipped around that time. But after that, steadily increased and dipped again during COVID time, as you can see. And that's also saying that public, this is a capital formation that is also related to the investment. So there are 4 things, 4 components of GDP. I'm sure many of you know already. Major components, I should say. There are many ways to actually compute GDP. Recently, we have been taking classes, so I don't know whether I've learned enough to talk about it. These are basically called national income and accounting. So there are major 3 ways are from income perspective, from production perspective, and from expenditure perspective. So GDP can be computed from all three different ways. Okay, so the method we have used here is from expenditure perspective. The expenditure perspective, there are four major components. Four major components is government final consumption expenditure, which is called GFCE, and private final consumption expenditure, which is called PFCE. PFCE includes household and also non-profit organization. Okay, so which sort of supports households in some. So um, so PFCE plus GFC plus capital formation GFCF. Okay, this is another one, which is the investment, basically money, that how much you invest in infrastructure, etc., etc. And then trade balance. I mean, export minus import, etc. That's trade balance. There are other small components are there. We are not just interested in that. These are the four major components of expenditure way to compute GDP. Okay. Okay. So this is the real graph for those things, and this is the inflation we computed through the GDP deflator. So percentage basically changes in this. As you see, it's kind of up and down, and I don't know. So this is we didn't take CPI or anything like that, because that actually depends sometimes on the basket to basket. It changes the basket. So we use this one as a proxy. So, and the repo rate and the bond rate, as you see that this is a sort of just to demonstrate that actually the bond, this is the interest rate, is basically bond rate. So Reserve Bank's policies, or the central bank's policies, the repo rate when it goes down, it sort of has some kind of matching in these things. As you see, it's a that's why repo rate is quite important. You remember the bond rate is not under government control, or neither the Reserve Bank control, only the repo rate. But that's why you see that it is kind of related in that sense, in the macroeconomic sense. So again, so causality. So we sort of tested that whether those variables which we have taken earlier, the state variables and policy variables, importantly, whether they actually they are causal. That means whether their changes actually have some kind of impact on the state variables or not. So there are some tests which is granular causality. Again, we have done those things individually, although they don't. I mean, they don't really make changes to the all state variables. But if we take it collectively, they actually showed that it is causal to the state variables. That's why we have chosen those four state variables, and that yeah. We took as a pairs, as you see that pairs, and there's yeah, this GDP diff. So these are the rows are actually the state variables, and the columns are all other variables, whether they cause each other or not. So as you see that in fact individually they may or may not, but the collectively will show it later that yeah, the null hypothesis is that control group do not grandeur cause the state variables, right? Control group is I, G, repo, and H. So I diff, G diff, G diff. Basically, we took the log difference. That's why you're seeing the diff here. So they are not separately causing the state variables. However, so yeah, so however together they actually cause the I mean, they actually make influence in the state variable. That's it. Together is important. So we construct War model using this, and then we go to model selection. Basically, we decided how many lags we should be taking. So here we have used the AIC and BIC models, and as you see clearly that in the BIC it is 4 or 5 around is the minimum. Is the around 4 is the minimum most here. 6 lags are here, and this line is for 6 lags, and right, lag 2, and so these 3 lines are for lag 2, lag 4, and lag 5, exogenous lags and endogenous. Okay, so 3 lines. So exogenous variables, we have plotted 3 lines. Okay, and for endogenous lags, we have taken this tip means minimum occurring is 4. So basically, we have taken the endogenous variables means all state variables. So we have taken the 4 lags as the minimum. So we haven't taken the 8 years lag. So we have minimized that way. So this is a model selection problem we have used here. And also AIC is saying that, as you see that all 3 have sharp decrease and then kind of flat and then little decrease here. So we have restricted ourselves into 4 to 5 lags here and use the 4 lags of exogenous variable there. So that's the error, etc. For stability purposes, we check the errors. So let me go to the shock behavior. Yes. So here the shock means basically the effect of increased government spending. So we wanted to see that what happens if we suddenly increase the government spending, what happens there. So at t equal to 0, we sort of put the change, then immediately you see that some changes happens in the GDP. It decreased a little bit and then started increasing, so sort of recovers afterwards. And similarly, government bond also decreases a little bit and then changes afterwards. Inflation actually steadily increases, and after government spending, that means if government spends more, inflation will increase. That's the kind of things are showing there. And exchange rate is kind of not really dependent that much. I mean, it sort of increases a little bit and then decrease and then stabilizes afterwards. So this is the repo rate shock. Again, we have tried and things like that, basically trying to show the influence of those repo rate change. Again, here unexpected increase in repo rate. So if we increase the repo rate, GDP decreases because not enough spending in this. And okay, and then as you can see, exchange rate, etc., similar behavior, and the inflation actually dies down a little bit. That is important, and then afterwards slowly increase. Repo rate increasing, inflation dies down, and interest rate also, government bond interest rate also dips quite a bit. Okay, so how much time I? Okay, good. So I'm in the last phase now. So optimal policy variables. So anyway, these are stacked ones, as we said, right? And this is the cost function. Okay, cost function, there is only something I should mention. Here, as you see that I put against the GDP, I put 1, and then I put lambda 1, lambda 2, lambda 3. This is kind of important. We do not know what should be choice of lambda 1, lambda 2, lambda 3. Okay. The way to find out is to do the sensitivity analysis or through another macroeconomic way of doing the theoretical justification for this choice of lambda. Basically, these are really relative importance of the interest rate, GDP, and the exchange rate, and the other one. I mean, the what's the pi was reflecting that. Yeah, the fourth variable we talked about, expenditure, right? Expenditure. Yeah, I think pi was right. So anyway, so these things are relatively important. So we sort of chose this one according to our judgment here, and we sort of varied a few of them to see the sensitivity also. But some more need to be done further in these directions. Yes, and we checked finally that whether this one in the quarter, 12th quarter, 13th quarter, 14th quarter, 15th quarter, which is related to 25, 26, is bigger than 5 or not. So that's the checking we have done. Right. So here are the results. Okay. Black line relates to quarterly growth, and that left index is related to the quarterly growth index, and the right index related to the annual growth, the green ones. So as you see that you can reach probably 6 trillion and annually, and that would relate to the final quarter to be around 1.6 trillion there. Okay. So if you target that, so what would be the fallout? Let's see. So optimal variable paths are like this, right? Inflation, okay, that's right. Inflation is another state variable which was related to pi, I think. Anyway, or P, it should have been P. Right. And so these are the basically exchange rate as it dips down almost to 2% there. Here the control variable path. Okay, so let's look into control variable. So you see that it is coming to the hugely negative. That means the percentage, that means you have to sort of money supply has to be goes into positive and negative hugely. That means it's a almost percentage change log difference. It is so almost like a log of the previous to log of the current is the bond means say almost how much percentage near is a log of P1 by P naught. Log of P1 by P naught, if it is 1, so it is like a 2 times 2 point E. 1 means is E, right? Log difference is 1 means it is E. That means 2.7 times of the previous. So that much money supply increase or that much money supply decrease, that's a huge kind of difference there. As you see, log of the log difference scale. Similarly, repo rate is, you see that repo rate is actually rate itself, not the log difference. Repo rate coming to the negative 5%, which is not actually supposed to be. Repo rate coming to negative 5% implies that you give freely to the bank and add 5% to that. You supply, you increase the supply at that rate that whenever bank wants money, so you give the money and you increase 5%. And that's the, in sort of loosely speaking. So negative, you cannot do the repo rate, right? That's the important part. So lending cannot be, lending rate cannot be negative here. And investment also, investment again the log difference. So you actually go almost like 2 times it, three, almost like 400 times. I mean, 4 times the previous things or 5 times the previous thing as opposed to the also 4 times the negative way. So hugely fluctuating this investment. And repo rate also almost no. So that means what I'm trying to say is that suppose to reach this one, this is the unconstrained thing, you have to sort of go to an extent where it is not sustainable in a way. You cannot do the sustainable way of reaching this target. So then we sort of just one or two more slides, then we sort of constrain these things that we sort of say we cannot go beyond this limit. And so in the money supply, In the repo rate also we cannot go less than 0.115, and investment also we cannot be lower than this. So if we restrict these ranges, then what we get is somewhat target is nearly reaching, whereas the nearly 5, nearly 5, not too bad. So what do we get there? In control things, exchange rates are, repo rates and base money and investment. Let's see what is repo rate. We have said that it cannot go less than 0. So we have restricted that. That means we can actually lend the money to the bank in the 0 rate there in lots of things here. In the going towards this one is nearly there, and also investment purpose, you actually goes to hugely because it's a 0.3 and plus 0.3 to minus 0.3. We have restricted that, so that way it's showing not too bad. And base money control, that means supply side, that also we have restricted that one. So here it's showing not too bad if we restrict this one, so reasonably enough and almost there. Conclusion, we know that under constraint setup, sustained growth, inflation not maintained that much. Moreover, interest rate on bond is quite low. And in constraint setup, cost to go coefficient, that the MKDK can be recomputed considering the boundary condition. Here we have actually kept this solutions MKDK, FK as same, but restricted only the control part, which we have to again changes the coefficient. And one possibility of achieving realistic goals on the policy variables are changing the lambdas, etc. Coefficients that need to go. So that's more or less the what we have done so far. And there are more to improve here, and there are computationally some more challenges are there. So I think thank you. Patient.
Thank you, Gopal. So something very strange. We may catch some high secret conversation between our security at IAC on this receiver here. It's a bit strange. But thank you again. Yes. I think Gopal can probably translate. I mean, I don't want to hand it back. So people in the other room, I don't know how many are there. They can also ask questions if they turn on their mics. So is there any questions?
We should stand side by side.
So I have a couple of questions. One is was this choice of picking this 2021, including 2021 data conscious, because there was such a steep fall in
the question is that is the choice of 2021 data was consciously we have chosen because we know that there are steep falls in that side. We actually didn't have much choice, as I mentioned, that we had 25 years of data. That is, first of all, that's the constraint, and that's of course too low according to all of our colleagues in econometrics, etc. We said that it's pretty much very low amount of data, only 100 data points. And secondly, the target, what we wanted to see is the another 4 or 5 years time. So that should start from somewhere. So it cannot start from arbitrarily. So whatever the economy is, so from that time onwards. So that's why we have chosen. It depends on the policymakers, really. As you see, the policymakers' decision, the control variable was very erratic, as you saw that, right? It is somewhat like showing as if that you have to higher the money supply, higher the repo rate, etc. And again, next time you have to decay. So can the policymakers take that kind of erratic mathematical decisions? It is really mathematical decision, right? So whether they will subjugate to that kind of decisions, we don't know. Cannot predict. Nobody can predict that. So whether we can convince somebody or they are convinced to this one, it's beyond our control. Those are optimal paths. Exactly. So basically we can further compute it, whether we can constrain in certain narrow band, we can further constrain it into narrow band. That's what we did the second one. We have constrained into narrow band. We can actually see what are the policymakers ideal narrow band can be. And then we can actually, what we have done here is that we actually made a formulation so that we can compute whatever their constraint is. And then we can run the program again and we can see whatever the optimal path where we are reaching there. That's what we can say right now. Yeah, that's perfectly math. I mean, the data we have basically what you are saying that if we sort of ignore the last 2 years data, if we ignore the last 2 years data and sort of impute, basically there is something called imputation, impute the last 2 years data based on the previous data series. So, and then use that series to do this one, it's perfectly all right. Mathematically or the computationally, we can surely do that. I'm not sure whether it would be realistic, but yeah, we can surely do that. It would possibly lead to different one. Yeah, it would possibly lead to, because wherever you are right now, it would sort of take from there, and wherever you would be then, it would be taking from there. It would be leading to something little bit different one, definitely. It is the real data thing. So that's why uh, any data change you do, it will reflect that one. So just a real data. Yeah. Very nice question. Actually, as you say that individual variable may not cause all those state variables, but together they do. That Granger causality test actually showed that individually they may not cause all these state variables as well, but together they cause the state variables. That means together means we sort of took the money supply, we sort of took the repo rate, and then government expenditure. So government expenditure comes into play. So whenever government expenditure increases, repo rate has to also increase to adjust the inflation rate. So that's why they are connected. And government expenditure has a lot of influence on the exchange rate as well. I mean. Right, right. Basically, no, no, there are a lot of, yeah, it's a, yeah. Thank you. Thank you, everybody. Double click. Fine. First, yeah. It's not.
You don't hear it. You open this? No, no. Something has. Yeah. You can probably hold it in hand and do that. Yeah. Okay. Yeah, this is looking bit odd because in between what's happening you don't hear. And we'll just use that one. Just to be updated. We'll just hold it. And otherwise, check now. Yeah, I know. There is one more. It's on the. It's on. Yes. If that is another column. We have another column. That will go. No, but then the teams has to detect both. Yes. So not tested. Just use one more. We didn't test the other. Because that looks.
This one. Okay. All right. So we'll start our next talk. The next speaker is Suresh Kumar, who, as you all know, is a student of Mrinal. So, and Suresh is from IIT Bombay, and he'll be talking on a multi-parameter nonlinear eigenvalue problem and risk-sensitive non-zero sum stochastic games. Suresh.
This is it. You can hear me now. Others, the online can hear me, isn't it?
Yes.
Yeah. So I'm just talking about actually a multi-parameter nonlinear eigenvalue problem, and the risk-sensitive non-zero. Its connection with risk-sensitive non-zero sum stochastic differential game. So it's in fact a joint work with Professor Ghosh, and then yeah, it's in fact it's a family affair. So so two of his students and one of his grandchild. Okay, and then and one more thing, two of his students are actually his first student, and then his last student. Both are here. Okay, so yeah, more later evening. Yeah, I just because it's becoming too long, so I just wrote. Okay, so so let me just briefly describe what my plan of this talk is. First, I will tell you what this multi-parameter eigenvalue problem is. Then I will then parallelly describe the non-zero sum risk-sensitive stochastic differential game. And then I will tell you what are the main result and indicate some of its proofs. Okay. So what we are going to start with is actually we'll just look at a parametric family of linear operators L of u1 u2 given by actually just doesn't work, isn't it? This pointer is not there. Okay, so given by this second order linear differential operator with the two parameters u1 and u2. So where ui's are actually going to take values from P of Si, which is going to be the space of probability measures on a compact metric space Si with the weak topology or the Prohoro topology. And where this BAs are actually, well, I will come back to that because this is a directly connected with the stochastic differential equation. And then these operators are in fact going to be the generators of actually those stochastic differential equations. So what we do is actually we are this B or the drift, the so-called drift vector is actually going to be a function from RD cross the parameter set U1 cross U2 to RD. And we will be using that in a relaxed framework in the sense these are actually going to be the averages of some other functions whose domain is actually RD cross S1 cross S2. So where SIs are actually this the so-called compact metric spaces. And then what is our A is in fact sigma transverse. and where sigma is actually going to be the whatever that underlying SD is diffusion coefficient. And then we have a cost function. So this is, we call it actually the cost function because it's this problem I'm going to discuss is actually going to be directly connected with a uh, differential game problem. So it automatically will be having some cost function, which are actually called Ri, which again, it is in the relaxed framework. That means they are the averages of some other function, which is defined on this Rd cross S1 cross S2. Okay, so what I will first do is actually I'll just tell you some of these basic assumptions I'm just going to use. So these are very standard assumptions. We will be assuming that this B bar sigma are continuous and they are going to satisfy the local Lipschitz continuity. For B bar, it is actually going to be next, which is uniformly over actually the control parameters U1 and for since it is B bar, it is over the parameters S1 and S2. And then again, Ris will be assumed to be continuous and bounded from below, and again, which is going to satisfy the local Lipschitz continuity in X uniformly over the other parameters S1 and S2. Because here I'm looking at Ri bar. So Ri bar is actually the original ones, and then you will be taking the averages, which gives you the Ri. And again, we will be third condition is actually linear growth condition. And fourth one is actually the local non-degeneracy condition, which these things are actually quite some very standard conditions. We'll be putting it on actually that the generator, the parametric family of linear differential operators we have seen in the first slide. Okay, then what we will be doing is actually we'll be just looking at some collection of control sets, which are actually going to be UI from RD cross RD to UI, this calligraphic UI, which you recall that it is actually probability measures on SI. And where, so this is a collection of all measurable maps. And then we will be using metrizing. We'll be using a topology. It's a metrizable topology, and it can be characterized using this mode of convergence. So essentially, this is there in actually their book on that red book, which is like a Bible for us for the control. So, and then we call it again. There is a reason we will be calling this collection of all this control set to be actually the set of all stationary Markov controls. For the here I am just this I is something to do with actually the game, so corresponds to actually the player I. And then you can see that they are actually this is going to be compact under this topology. Now with this, so we started with a linear differential operator. Now what we do is actually using this stationary Markov controls, we can actually construct a family of nonlinear operators indexed over actually this UJs. How do we do that? The G1 U2 of F is defined to be, what you do is actually just fix your U2 and then in the original linear operator. And then what you do is actually and then take the infimum over actually the first parameter U1. And then similarly, you define actually for the you take your U1 and then take the minimize actually this L of U1 U2 plus R1 F over U2. So that gives you a two family of actually nonlinear operators. So where let me just tell you that the way you define this L U1 capital U2 F of X is 1/2 Aij del ij f plus bi x u1 u2 del f. And similarly, you will be doing the other one, and we will be using another linear differential operator, where what you do is actually you fix two of them to U1 capital U1 and U2 from the respective stationary Markov control. So these are actually going to be the set of linear and the nonlinear operators we are actually just going to use. Okay, then yeah. Which one? They are actually just measurable map. There is nothing random right now here. Yeah, these are the measurable maps. Yeah, that randomness we will come. We'll just see later. So here now everything is deterministic. There is nothing. But this has some meaning when you actually just get into actually this differential game problem. But of course, there is a connection there. Okay, so now for take G to be a representative of all these operators, and now we define actually a generalized principal eigenvalue as this. So see this definition is actually, I think it is actually just started with Varadan's idea, and then it was actually just been lot of work is actually being done for the linear case when G is linear. And when your domain is actually unbounded, then a lot of interesting things you will just see for the Dirichlet eigenvalue problem. And then this being extensively studying by Beretetsky and then Rossi in a series of papers. Okay, so we'll be just taking this. See, there are various other ways one can actually just define various other generalized principal eigenvalues are there, but this is the one which is actually going to really connect with our problem. Okay. Okay. So now what I will do is actually I'm just going to use some notations to just make things similar. So what I'm going to do is actually for a given uj, I'm just going to see, look at actually that lambda I plus of uj. I'm just going to define it as actually the principal eigenvalue provided, pretend that it exists of g uj uji. So here where I not equal to j. So what I want is actually my operators are actually either it is actually going to be g u21. G u21 or it is actually just going to be or G u12. So just keep that in mind. So I just where okay. Okay, so so lambda I plus is actually of uj. For example, lambda 2 plus of u1 is actually going to be the principal eigenvalue of the operator u g. I told I think g12. Okay, and now and then you define the principal eigenvalue for lambda I plus of u1 and u2 to be the principal eigenvalue corresponding to the operator L of u1 u2 plus Ri. You remember that we are actually just the linear operator which corresponds to these two stationary Markov controls. Okay, so let's actually just see what we can actually just these things. Okay, so now consider a map u1 u2 going into actually this pair of principal eigenvalues, which is defined on actually the u1 s1 sm cross u2 sm cross. And then I will just tell that this is a Nash pair if the following inequalities are actually just satisfied. So that means if now pretend that these maps are actually the controls of someone who is playing a game, and then what his payoffs are actually just going to be the corresponding principal eigenvalues. Okay, and then what I want to tell is actually if one of the player unilaterally deviates from his or her Nash pair, then he is actually going to get a something which is more here. So because we are minimizing it, because you'll just see that the way you define actually the principal eigenvalue is actually the infimum of certain quantities. Okay. Now, okay, so this is now the question. What I want to do is actually I just want to actually just look at what we can actually just see. I just want to. The Nash equilibrium is actually not the important thing. I want to actually just look at something else. I will just tell you that in one of the main results. Okay, so Nash equilibrium is actually it's a very I don't think that's a good game to actually just play, but this can be used to actually just look at actually the corresponding sensitive stochastic differential equation. Okay, so now let us actually just look at actually a different problem. Okay, so to this end, we are actually just going to look at a controlled diffusion given by the solution of a stochastic differential equation d of xt is equal to b of xt u1t u2t dt plus sigma of xt dt. So this is what I told. So this is the diffusion part of actually the equation, and this gives you the drift or the velocity vector, and then where W is actually a standard Wiener process evolving in RD, and then UI. Now let me just actually just go into the really the random setup. So where U1 is actually going to be a U1 valued process. Don't forget U1 is actually our space of probability measures defined on S1. U1 valued process, which is a non-anticipative functional of X. That what I want to use it is actually U1 of I of T. I think I should have used UI and UI to be UI valued process. And okay, so where UI of T is actually a function Fi of T, comma X of 0 to T. So that what it means is actually look at the solutions are actually going to be actually the paths are actually going to be the continuous. What you do is actually restrict the path up to 0 to T. And for some measurable function, which is actually going to be from Fi from 0 infinity across the space of continuous functions, RD valued space of continuous functions to UI. And then such a UI, we call it as actually an admissible control for the player I. And then we will be denoting this whatever this, what is it called? The math frac, isn't it? Frac. U to be the set of all admissible controls for player I. Again, one more typo. Okay, so this is the controlled theoretic framework we are actually. So this is what is actually called a controlled diffusion with the controls U1 and U2 satisfies certain admissibility condition, which is actually just given by this. Okay, so now I already told you that there is an Ri which is actually there in the background. Using that, we define some function Ri of x comma u1 comma u2 to be the lim sup of 1 upon t logarithm of expected value of e power integral 0 to t Ri of xt u1t u2t dt. And this is what is actually called the risk sensitive cost criterion for when the players chooses their actions to be u1 and u2. And then now the and again here again the concept of Nash equilibrium comes. You say that the pair u1 star u2 star is going to be a Nash equilibrium among the class of admissible controls. If again if the player one deviates from his the so-called optimum, then he is actually going to be see, because the idea here is actually you want to actually it's a cost, so you want to actually every player want to actually just minimize their cost. If he deviates from actually his pair from the Nash equilibrium, he is definitely actually just going to lose. So we and then similarly for the second player. So you just see that this is essentially what we have seen for the other case also. Now here the question is actually about here in showing the existence of whether it is possible to show the existence of a Nash equilibrium. Okay, so these are actually the two problems we will be considering, and then now we will actually just okay, just I'll just I need a little bit more notations. So here I am just going to define. So eigenvalues I have defined with the plus on the top. So here I will be defining lambda 1 x of u2 to be. What you do is actually just take the cost for the player 1 and then fix your u2 by the action by the player 2, and then take the infimum over all the action, all the controls for the player 1. So this is what is actually called the give if second player fixes announces his strategy or fixes his strategy, what is the best the player 1 can do. So this is so lambda 1 x u2 is actually going to be the best response for actually the player 1. And similarly, and then now just see that this is something like you look at if you look at actually the cost function, this is something everything is essentially the long term average is going to play a role. So where you start initially is actually in most of the cases not going to play any role. So what so here there is a dependence, but you finally you will just see that there is not really any dependence under some suitable geometric stability assumption. You will not be going to see that dependence there. So, but instead we are what we do is actually just look at lambda 1 of u2 to be take the infimum overall, the initial conditions you are actually just taking. Similarly, you are actually just going to define the optimal response for actually the player 2 like this, and then lambda. Just keep in mind that here there are these optimal responses. There is no plus on the top. For the eigenvalue, there is a plus. So keep that in mind. OK, so now what to it is in a relaxed setup. In a relaxed setup. No, no, infimum is what do you mean? I just no, this infimum is attainable. Yeah, it is attainable. So because the Nash equilibrium, finally you are actually just going to get is actually attainable. No, it is actually that it will be attained. Yeah. So when the next set of assumption, it makes that independent of x. Which one? Yeah, the same. So what I'm doing here is actually I'm just. Which one?
There should have been an X also.
Lambda 1 of here. No. There is no. So I'm just taking the infimum just to avoid that. OK, so finally it's not. See, if you see these questions, suppose see because we are actually looking the situation in a very nice world where non-degeneracy condition is there. See, so, yeah, that is, there is an x. Infimum or x, no. So that no. Finally, when the next set of assumption, this is not, this becomes redundant basically. You don't need, but when you pose the problem, it is not really. In fact, in principle, it can depend upon x, but we put actually just put a lot of conditions so that that's not happening. Especially actually we started with the local non-degeneracy. Suppose it is non-degenerate, then definitely you expect it's something like a reducible situation for a Markov chain. So the initial condition. Yes, uniformly ellipticity. Yeah, that's where you need. Otherwise, yeah. Yes, that is the principal eigenvalue. No, it exists in certain. It will exist. So that lambda pluses are actually the principal eigenvalues. They exist. No, you mean yes, and you mean actually there is no. You will have you will be having a corresponding positive eigenfunction. No. Yeah, yeah, I'll just tell you. So what was that? Lambda plus is actually going to be the infimum of every lambda belongs to R such that you need some phi positive and which is in some nice tabular space so that g of phi minus lambda phi is less than or equal to 0 almost surely. So in fact, this principal eigenvalue under, of course, you need some condition. Principal eigenvalues are actually going to exist. And when it exists, in fact, there exists said positive eigenfunction where equality holds. Yeah, it is there. Yeah. No, no, we need to work out those things. OK. So we need these two set of assumptions. So this essentially now it is actually being something called the geometric stability assumptions. I'm not going to ponder too much into these conditions. So this is what we are actually just going to use. Okay. For example, so this for A1, so these are actually just two different set of conditions. One you will be using when your coefficients are bounded, that is actually this part. And then when you have unbounded coefficients, then you will be actually this using the second set of conditions. And then maybe I will just skip this. How much time I have? Okay. So these are some very standard examples. Okay. And then we will be assuming this something which is right now unavoidable. We will be assuming some separability assumption in the sense that this drift and diffusions are actually just being separated by the controls. Okay. Then comes actually our first theorem. So assume A1 and A2 without the separability assumption. Then what you can see is actually for each U2 in U2SM, we can indeed see that this lambda plus of U2 is in fact going to be infimum over all U1 hat of lambda plus of U1 hat U2. So this is something maybe interesting, this result, more than actually the existence of Nash equilibrium. What it tells you is actually the following. So you look at this corresponds to the principal eigenvalue of actually the linear problem. And then G corresponds to you are actually just taking infimum over a parameter set. Then what this tells you is actually this is not exactly what I want. I want something which I need to actually just work it out. What you can see is actually the principal eigenvalue for the nonlinear problem. You can actually see it as actually the infimum overall the principal eigenvalue for the linear problems. Okay, linear operator. Okay, so I would, in fact, I would like this infimum to be replaced with the infimum over instead of actually this over all the measurable things. Instead, it should be something like U1 belongs to the parameter. So I think that should be need to work it out, but I don't have it right now. But this comes out. This part will come out. And then second part is actually you assume A3 and then you can actually just see that there exists a Nash equilibrium for the that fictitious game problem for the principal eigenvalues. So, yeah, see, whenever you see two controls, it corresponds to the and a plus it corresponds to the eigenvalue for the linear problem with two. And then when you see only one, it corresponds to actually the for the nonlinear problem. So that's the way you, yeah. So that's why. So it comes as actually infimum. So so that's something which you can actually observe here. Okay. So second part is anyway is more interesting is actually in fact the real game we have actually there. This first part is actually quite interesting. Okay, and then so this is actually going to be the then what you can see is actually under this set of three assumptions, the sensitive the differential game problem I described. You are actually just going to have an existence of a Nash pair. That is the second. This there is no plus, no plus. So that that's okay. Okay. Yeah. So, okay. So what it tells is actually that they coincide. See that sensitive value coincide with actually the with the principal eigenvalue. Okay. See, that is the reason this is the appropriate definition of the principal, at least for our thing. This is the appropriate definition of the principal eigenvalue we should be taking. Okay. And then and this in fact will imply that because you already know that theorem 1, you already have the existence of Nash equilibrium. If they are same, then that has to be the Nash equilibrium for the original. So, so what? So I will just tell you what are the results we are using. So one thing is actually a nonlinear version of actually the Crane-Rootman theorem. This is being used to actually just show the existence of the Dirichlet eigenvalue problem. For actually any nonlinear operators, we are actually just using it. So this is one of we will be a consumer of that result. And then so here we will be having one result which can be proved. So this is almost similar to actually the result which is actually just taken from actually this Quas and Zirakow. Which is about, it's a paper about actually the study about actually the principal eigenvalue problem for nonlinear. In fact, yeah, nonlinear operators. In fact, they do for actually that non-convex generators also. So it's a mild. So this result essentially taken from them with a mild modification. So this we will be using. In fact, this is actually being used. This result you will not see in the sketch of my proofs because this essentially being used to prove the simplicity of actually the principal eigenvalue. And then now, so what our method is actually, it's method what we are going to do is actually first you look at all these eigenvalue problems when you have a essentially you look at actually the balls of arbitrary radius and look at actually the Dirichlet eigenvalue problem. And then what you do is actually then you just make these balls larger and then somehow use some approximation arguments to show that you lead to this is actually just going to lead to the original eigenvalue problem. So that's essentially the method. Okay, so what you do is actually along the similar lines define the principal eigenvalue problem, and then one can actually just see that this second theorem tells you that for U which is in UJSM and D a bounded smooth domain, one can actually just see the existence of actually the principal eigenvalue. That's so here the psi corresponds to the corresponding thing, eigenfunction, which is in fact positive. So I just missed it there. Yeah, it's there, psi positive. So let me just see the method is I told you that what you need to do is actually you need to just cook up some map here on an appropriate space. Here we are actually it's a Dirichlet one, so you'll be using C0D to C0D, and then what you do is actually just use various inequalities, prominently the Harnack's inequality, and then get some this second order bounds, and then now there are stated conditions of Crane-Rootman is there. Just verify all these conditions and then get an eigenvalue there and then translate this into the eigenvalue for the problem. So this is roughly the method we will be seeing. And then what you need to do is actually just use the theorem I just mentioned. You can see that it is simple, and then little bit more work you require to show that in fact this the one which gives by actually the Crane-Rootman is actually going to, in fact, it is actually going to be the principal eigenvalue which you are looking for. So that that's pretty much the idea of actually the proof. Then what do you then once you have actually the one for actually the Dirichlet problem, what you do is actually just we can actually just we'll get another one which is actually for the eigenvalue problem for all of RD. And then what you can just see is actually it is going to be simple, and just see that first you can actually just see that this eigenvalue is actually going to be less than or equal to the value of actually the sensitive problem. And then how much time now? Almost. Okay. So I will not. I told you that the idea is actually just start with the Dirichlet eigenvalue problem, and then you need, okay, of course, you need to actually just work out many things and then pass to the limit. So that is what the hard part of the analysis. And then let me, I think it's not a good idea to do this, but But that essentially that is the idea. And then so to do the next part, we need some representation for actually the corresponding positive eigenfunction, which is actually which has a probabilistic representation like this. And then from there you can actually just show this. So this in fact in particular this will imply whatever I was telling you that lambda 1 plus u2 is in fact equal to infimum over all. From here you can actually just work it out that it is in fact going to be the infimum over all lambda plus of u1 prime u2 where u1 prime runs through all the stationary Markov controls. Okay, this again I will just skip. I told you now this you go get into actually the Dirichlet eigenvalue problem and then get the representation there and then pass to the limit. Okay, so and then to get to the Nash equilibrium, what you need is actually one need to actually just because see there it's what we are going to use is actually a fixed point argument. So there you need something called an upper semi-continuity of a set valued map. To facilitate that, what we need is actually we need a continuity of this map. And then once you have that, then the proof comes. So what you do is actually you look at actually this set. This is the set valued map I am just talking about, and then show that it is upper semi-continuous, and that will indeed will imply that it has a fixed point, and any fixed point of this this map is actually going to be a Nash equilibrium. So that's more or less actually the proof. So so essentially the proof for the Nash equilibrium is look at actually the see this you can actually just tell that this is the optimal response map with replacing you what you are going to do is actually among the optimal responses you look at actually those controls which has actually that attain that optimal responses and take that upper that set valued map, show that it is upper semi-continuous, and that's it. That gives you actually the Nash equilibrium. I think that that more or less, and then once you have that, then you have actually the Nash equilibrium for the original resensitive control problem. I think that's it. Yeah, I think sorry if that I just took more time.
Hold it in our hands. Are there any questions or comments? I don't know if there are people in the other room who may want, or people who are online can also unmute themselves and perhaps ask questions, right? Okay, if not, let's thank Suresh again. So we will meet, we will start at 11:20. Yeah.
Oh, okay. I was actually just, I thought that I'm running very